Google JAX is a library that enables transformations of array manipulating programs written with a NumPy-like API. In this video, I demystify what this means by a series of examples. You can think of JAX as differentiable NumPy that runs on accelerators. To install JAX in your Python environment, you can use pip install JAX. After installing JAX, you can import JAX and JAX.NumPy and use APIs similar to NumPy for JAX.NumPy. For instance, you can use the arange function and assign a vector to the variable x. Since I have passed the value 10 to the arange function, I get a vector with component values from 0 to 9. You can also pass the variable x to the type function to get the type of the variable. JAX grad function is a fundamental feature of JAX that allows you to transform functions. For instance, I define a function that takes an array and returns the sum of the squares. Applying JAX.grad to sum of the squares will return a different function, namely the gradient of sum of the squares with respect to its first parameter x. In the mathematical notation, the x is the array and the xi's are the components of the array, and the variable n as the upper band of the summation is the length of the array. You can think of JAX.grad by analogy to the nabla operator from vector calculus. Given a function fx, nabla f represents the function that computes f's gradient. We can also take derivative of multivariable functions. For instance, I have defined the function sum squared error. By default, JAX.grad will find the gradient with respect to the first argument. For instance, over here, sum squared error dx will be the gradient of sum squared error with respect to x. To find the gradient with respect to a different argument or several, you can set the argnums, in which case you pass the index of the arguments you want to calculate the derivative with respect to. Sometimes you need to find both the value and gradient of a function. JAX also has a function which returns a tuple of value of the function and gradient of the function. Sometimes we want to report some intermediate results obtained in computing the loss function. But if we try doing that with regular JAX.grad, we run into trouble. This is because JAX.grad is only defined on a scalar functions and our new function returns a tuple. But we also need to return a tuple to return our intermediate results. This is where has_aux comes in. Has_aux signifies that the function returns a pair, output of the function and auxiliary data. It makes JAX.grad ignore aux, passing it through to the user, while differentiating the function as if only out was returned. The most important difference of JAX from NumPy is JAX is designed to be functional, like functional programming. The reason behind this is that the kinds of program transformations that JAX enables are much more feasible in functional style programs. The most important concept to understand in functional programming is side effects. A side effect is any effect of a function that doesn't appear in its output. For instance, I have given an example of a function modifying an array in place. The side effectful function modifies its arguments but returns a completely unrelated value. The modification is a side effect. In addition, you should be aware that JAX arrays won't allow themselves to be modified in place. So if you try to modify an JAX array in place, you get an error saying that JAX arrays are immutable. Now we want to implement our first training loop using JAX. For this purpose, we solve a linear regression problem. Our data is sampled according to the equation y is equal to w true times x plus b true plus epsilon. We sample our noise, which is epsilon, from a normal distribution. We can plot the equation for y using plt.scatter. We will use a single array theta to house both parameters, that is w and b. The loss function j is function of x, y, and theta, and to optimize our loss function we need the update function. How do we optimize our loss function? The answer is using gradient descent. At each update step we will find the gradient of the loss with respect to the parameters and take a small step in the direction of the steepest descent. This basic recipe underlies almost all training loops you will see implemented in JAX. The main difference between this example and the real training loops is the simplicity of our model. Don't forget to like this video and subscribe to my channel to not lose future content on Google JAX. As always, see you all later.